All right, let's now go through some reminders. Your assignment number 2 has been released. That one there is just about simply linked list. I think the instruction there is pretty clear, not much to add, but I do really want to emphasize 2 things quickly. There is certain things about recommended studies, optional. So the problems that we're going to discuss in the lecture are more foundational updates for the simply linked list so that you got a technique or the skills to really trace or to develop the more advanced algorithm. But if you want to see something slightly harder than the problem we solve in the class, you can also go there, right? It's optional. You'll see the links on the instruction PDF. And this one here, I really want to emphasize, guys, only once, right? This part here is required, no option, okay? So I'll show you where to find them. If you go to the assignments PDF instruction there, there will be a section about required. But as for the slides, I'll show you where you can find them. If you just go to the arrays and linked list over here, and then you go to slide number 33. All right. Oh, sorry about that. Not that one. There we go. If you go to slide number 33, it's something about generosity in Java. I don't necessarily assume that you learned about it in 2030. Well, for example, I didn't cover that in 2030 last term, right? However, generics is not difficult to catch up, given that you learned about very deeply about polymorphism, dynamic binding, and typecasting. It's not difficult for you to catch up. The generic parameter will be required for you to complete assignment number 2 and also to complete programming test number 1 and 2 as well. So you definitely want to learn it as soon as possible. Ideally, you want to catch up with all the basics over here from slide number 33 to 36. 4 slides, right? 33 to 36, 4 slides. And starting from next Tuesday, maybe the second half, once we finish the singly linked list, we're going to do some doubly linked list, and we're going to see more about generic list. And from that point, I'm going to assume you already understand about generics, right? So you really got to catch up with the stuff, right? So in the assignment instruction there, and also here, you will see the video link. So they are very good quality video presented by myself. So it will be just the same if I were to present them live. So just watch them, study them, and make sure you learn the concept. If you got any doubts about generics in general, reach out, and then we'll talk about it. All right? I'm going to rely on you. Right? Again, it's going to be from slide number 33 to slide number 36 about generic parameter. All right? That's something you really want to pay attention to. And then let's now move back to the next item. Okay. Assignment number 1, solution. And then take a look. Let me know if you got any trouble understanding anything, or you just want to redo it. Right? That might be good practice too. Split array header, I'll release the solution over the weekend and maybe with some tutorial video, short one, to guide you through a little bit about the solution and some insights. I'll do that. Hopefully Sunday or maybe early Monday, something like that. Okay, I'll reach out to you. Notes template, the same place, right? Office hour, TA contact, just the same. All the resources there. Any question about the course in general? And early next week, maybe about Wednesday or so, you're also going to receive a detailed PDF guide about programming test number 1. I'm going to talk about the formats, also expectation, and also about some practice question for you as well. Right? You can expect that. Wednesday the latest. I just need to also confirm with Jeff and Sunila just to make sure everything is consistent across the sections. But it will be something very similar to your assignment number 1 and number 2. Right? So you definitely want to tackle your assignment number 2. If no further question, let's do a quick recap, and then we'll move on to more about simply linked list. Cannot finish today, but we definitely, hopefully can finish that on Tuesday, so you'll be completely ready. Okay. So last time we started with this exercise over here, and this one here just about designing some hybrid algorithm combining insertion sort and selection sort. So I may not dive into details, but just remember there are 3 parts for this kind of question. Part A, just based on the description over here with no code, you have to somehow take a guess or informed guess about what the most accurate asymptotic upper bound is. Part A. Part B, you're going to justify your answer, maybe using some formulation about the arithmetic sequence, whatever, right? You're going to justify that. That's part B. Part C, some algorithm may not work for all the inputs. In that case, you have to somehow describe, maybe informally, under what circumstances is the input not going to work for the algorithm. We kind of gave you one example that works and one example that doesn't work. And ultimately, you want to feel comfortable about using what you learned in 1019 about practical logic, using universal quantification, right, etc. So far we have seen a few universal quantification already. Whenever I can use them to specify idea, I'll use them, so we just get more exposure. But you definitely should expect questions like this, also in the assessment. All right, any question about this hybrid algorithm here? All right, study that, digest it, and then let me know if you got any question there. All right, and then we talk about singly linked list. All right, we did some very quick, well, I would say pretty thorough visual introduction as well. Let's briefly recap the concept. We talk about a chain of connected nodes. And the way we connect each node is by using the next reference. That was really aliasing, because you might have more than one references pointing to the same node. It's very common. Sometimes you just have to introduce extra variable to help your algorithm to really execute. That's something we'll see today. Very common pattern. And we talk about here linear versus nonlinear collections, right? Talk about array and linked list. They are linear. And the trees that we're going to see later, hopefully soon after reading week, it will be nonlinear. Okay. And we talk about the possibility of null pointer exception, right? So when you do assignment number 2, don't feel too frustrated if you run into null pointer exception very often. It's normal, right? You want to minimize the chances of getting that. So hopefully you wouldn't have any during the programming test. And we talk about absolute indexing versus relative positioning for the two, right? So for absolute indexing of array, constant operation, just calculating address. For relative positioning, it's about starting from the head, and then you cannot get around, but you have to use as many next references as necessary to really get to where you want to. And in the worst case, where you want to get to may be very close to the end of the chain, which will be the size of the nodes, the size of the chain, and linear operation in general. We'll see more example about linear operation, not sure today, but maybe Tuesday, right? We'll see more. And this page here is actually very important. We kind of go over 5 different operations, about 3 inserts: insert to the front, insert to the middle, insert to the end. And also removing from the front, removing from the middle. And removing from the end, we'll talk about it a little bit. You can also try to do exercise. All these 5 operations, or 6 that we talk about here, they are the fundamental ones to really implement. And the way we kind of change the references, the way we create new nodes or create new temporary variables, they are basically what you got to do for any algorithm for singly linked list. Right? We're going to see more coding example today. But if you already kind of understood what we said last time, today shouldn't be too bad. Right? We'll see. And more Java today. All right? We'll talk about 2 classes. I think that, yeah, that's the last page we had. So very quick recap. So we got 2 classes over here. We got a node class where we got 2 attributes. We got elements, we got next. You can assume that the node class is going to be pretty much stable. We're not going to add too many things into it. Just the 2 attributes over here. And we got the constructor and then accessor and also mutator, right, for the 2 attributes. One thing to know very quickly, and we'll see that right away. The node constructor over here is going to take the data and also the next reference. And what you really pass over here is going to impact how the node is going to be initiated. That's something we'll see, right, in a moment. We introduce another level here, singly linked list. Let's say you already got some node over here, maybe a chain of nodes, etc. You're going to have another layer called singly linked list. That one there is going to store all the auxiliary information about the list itself, right? Not just the nodes. So the one we're assuming we have to begin with just head, right? We're going to see more attributes. There will be a principle called trading the space for time principle, which we're going to see a little bit later today. And in the beginning, the singly linked list has the head pointing to null, but you can also set it to be the beginning of the chain, right? That's also something we'll see. All right, you want to get yourself very familiar about what attributes are available in these 2 classes. Just don't get yourself confused, right? So these are 2 separate classes. Guys, any question about these 2 classes in general before we dive into coding, which is important? All right, let's now see some coding. The next 4 pages, I want to talk about how can we construct lists in general. okay? Without worrying too much about individual accessor or mutator just yet. Just how we construct the list, just get some intuition, right? And also we can see some reference aliasing manipulation, okay? All right, the first one we're gonna look at will be how we can build a chain of nodes. For now, don't worry about singly linked list class, okay? Let's focus on just the node class, just that one there. And just to remind you, we got these two attributes, elements and also next, all right? And the constructor that we're gonna use will be this constructor here, especially we're going to pass the next node for the new node that we are passing, or we are creating, all right? Just remember that. Let's say we want to build a chain of nodes. This is the desired order we want to build. Conceptually, we want to build a node, a chain of nodes. Let's say we want to do Alan, followed by Mark, followed by Tom. Let's say that's what we want to have. And for the first example here, we are, well, for both approaches, we're going to use the constructor. But for the first approach, we want to use the constructor only. We do not want to use the setNext mutator. We don't want to use it. Let's say, how are we going to do? What you will find out is, if we want to do Alan, Mark, and Tom, the way we're going to create the nodes is going to be the reverse. Tom, Mark, and Alan. For now, just accept it for granted. I'm going to show you if you do it the other way, it's not going to work. Just in one moment. Okay? Let's now try to trace these three lines line by line, okay, quickly. So the first one is going to be the Tom, all right? So what we get is we're going to get Tom right here. So Tom is a reference to a node object, right? When you visualize the object, you can always put over here the node class. Each node we know has element and next, two attributes there. So we got, I'll just say E for elements and for next. And element here is easy, just Tom, right? It's going to point to a string, Tom. You can see the null over here is simply just the next, right? That means it's going to point to null. Whatever that's passed over here, n, is going to say next equals n. Well, if you recall a little bit from 2030, any attribute access over here has an implicit this, right? So it's like a this dot next equals n. So now what's this in this line here? Tom. So we are saying Tom dot next should be equal to n. So Tom dot next should be equal to whatever we pass as null, right? That's a basic tracing from 2030. I assume you're okay with that. Well, that's line number one, pretty straightforward. Line number two becomes a bit more interesting because we're going to pass the next reference here something other than null. All right, let's see how exactly it's going to work. So let me just say this one's blue over here. All right, and we are just going to draw that in a very similar fashion. Mark pointing to this node over here. It's a node object, right? The same class. I'll put node here. Elements and also next, right? The same structure, element and next. Element should be Mark. And then you can see here, Tom, right? For this one, let's do detail tracing one more time, okay? That means we are executing the constructor over here. So the this over here is going to be just Mark that we're talking about, right? So Mark.next will be equal to Tom. So you can think about Tom is replacing the arguments over here, right? So Mark.next, I'll put it here. So Mark.next equals Tom, right? This is what it will boil down into, right? Mark.next point to wherever Tom is pointing to. That's a very important connection that we're building. So we are doing two things over here. We're basically creating the objects called Mark, and we are connecting next of Mark into Tom at the same time. All right? One more thing to say, which you also want to think about. When you try to execute this line over here, the right-hand side is actually going to be executed first. And then the left-hand side is going to do the assignment, right? That's another way to think about it. All right, final line. That one there is going to be done in a very similar way. We don't need to do detail tracing anymore. So what I will do is I'm just going to create that node over here, That one there has also the node structure. And we got Allen in this case, right? Allen pointing to here, and then we got node, elements, and next. Okay. And the element, not surprisingly, just Allen, right? And here, do very similar. And this one will just boil down into Allen.next is assigned to Mark, right? If you think about this, will be just Allen. And the n over here will just be Mark. Right, similar. All right, right here. That's what these three lines will do for us. Okay, so what we have is a chain of nodes. Let's highlight it. We start with Allen, and then it will go to Mark, and then it will go to Tom. 3 nodes in the chain. And let's now review aliasing very quickly, right? Just give you one example. So think about how many ways are there that we can use to refer to the Tom node over here, right? Apparently, you can see you can either use Tom, or you can use Mark.next, or you can use Allen.next, right? So there are 3 ways. Okay, so once you visualize the diagram, it will be more straightforward for you to see the aliasing, right? I'll just write it down. Okay. So aliasing over here. So what we have is, for example, so Tom and also Mark.next, and also Allen.next. Right, so these are examples for aliasing. All right, good. And let's now try one more thing, right? So that's kind of the question from your fellow student in the previous years. They're wondering, given that we want to actually build this particular order, Allen, Mark, and Tom, is it possible to really create the objects Allen, Mark, and Tom? Yes and no, but let's say this particular solution, right? Let's take a look. All right, so this is approach 1 that we just saw. I want to give you something different. You tell me if that's going to work. So what I have is, I want to build Allen, and then Mark, and then Tom. From the previous page, we know that this works. But let me give you another one. What if I say I want to create Allen first? New node. And then, of course, I'll pass Allen's string over here. And I know that Allen should be connected to Mark. I'll put Mark here. And then I'm going to have node Mark. And then node over here. Mark. I know Mark should really connect it to Tom. Whereas Tom should connect to next to nothing. Equals new node, and then finally Tom here, null here. Do you think this alternative approach number 1 is going to work? Question here, what's going to happen at the runtime? Runtime. Null pointer exception?
Yes, null pointer, because Mark is not created at the time when we are creating Allen.
You think it's null pointer exception?
Reference error?
Huh?
Reference error?
Reference error is more like a runtime error or something else.
Like a runtime.
Runtime error. Guys, question is easy. Do you think it's going to be a runtime error or something else? Compilation error. All right? Runtime error means things compile. So you can run it and see if anything runs into exception, etc. But this one here, if I say runtime error, I'm tricking you. It doesn't even run. You can see, for example, over here, Mark here was only created after it's being used. Is it allowed in Java? I'm afraid no language will allow it, right? Okay, I'm pretty sure you know that, okay? Unknown variable. Watch out, all right? Compilation error, as your fellow student said, exactly right. right? It's not going to work. However, there will be an approach where we can still try to create these 3 nodes in that particular order. But it's just that you cannot really set these references right away. You may want to do that in a separate line, which I'll show to you. That's approach number 2. Is there a question somewhere? I saw.
It was just exactly what I was going to.
Thank you. Thank you. Good. All right. Let's now verify Diago's idea. All right. So this one is not going to work, right? Approach number 2. So we are going to create all of the 3 nodes separately, but now we're going to do that in Alan, Mark, and Tom. But notice that all the next references are just null. So we don't have the compilation error issue. And then we're going to call the set next separately. All right, let's do that very quickly. So I got green, blue, pink. Okay, we got green here, and we got blue here, and we got pink over here, right? Very quickly. So the green here, we are just creating just the same, right? We're going to create Alan. And then Alan is going to be a node. And then we got element here, right? Just save a little bit of time so you know what that value should be, right? I'll just say dot, 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 okay? The next over here, to begin with, just null. All right, so that's one here. And then we're going to get just another one, right? Let me just do some copy here so I can save a little bit of time. And that one there should be blue. Sorry. That one there should be blue, okay? And that one should be Mark. Alan, Mark. Okay, one more. I'm just writing here, a little bit too small, okay? So that one there will be Tom. And then we'll see how the references are going to be set up, okay? And that one should be pink. There we go. And that will be Tom. All right, we're creating all these 3 nodes in isolation. You can see all their next references just null to begin with, right? And then we're relying on the separate set next to help us, right? Just one of them. When you say Alan.set next, right? If you look at the set next over here, again, next implicitly got this dot next. So when you say Alan here, so this will be replaced by Alan. And the mark here is going to replace the n, right? So we basically have Alan.next should be assigned to Mark. So Alan.next is going to be assigned to Mark right here. Right? Similarly, if you do Mark.set next, Tom, it will boil down into Mark.next will be assigned to Tom. Right? So Mark.next will be assigned to right here. So we can end up building just the same chain. Because if you see that, so we start with Alan, go to the next, and then go to the next. We got 3 nodes still. So approach number 1, approach number 2 are basically equivalent. You can choose the one you want for programming assignments, so programming test or programming assignment, right? Doesn't matter. But you should really know the logic for both. Any question about this? Yeah?
If we switched Alan and Mark, like which one we set first, that wouldn't change anything, right? Like
Oh, I see what you mean. Yeah, in this case, no, it wouldn't. Okay. So what Ben's question was, what if we do Mark.set next? In this case, you wouldn't. So Mark.set next, you just set this one first, and then set this one next. Doesn't really matter. Yeah.
Can you also just declare the node objects above?
The node object above?
Declaration, like node Alan, node Mark, node Tom.
Oh, are you saying something like, I'm not exactly sure. Okay. Are you saying something like, I just declared node Alan, just like that?
Yeah.
Okay, you can do that, but it's just like other variable. If you simply declare the variable without initializing it, it just has a value null.
Okay.
Of course, yeah.
You can use that.
Yeah, of course, you got different possibility, right? Yeah.
What if in in the constructor for the second slot, you put the constructor for Mark. So Alan would be node Alan, comma, new node, Mark, comma.
I see where you're going. Okay. Brian is asking a very nice question here. Basically, what he's saying is we can use anonymous objects. Let's say Alan over here will be equal to new, okay, node. And we know that it's going to be Alan here, right? And this second place, I know that it's going to be some node objects. What I will do is I'm going to use anonymous object, which you guys learned about. Well, I'm going to share this also with Tuesday, with the morning section, right? This one is good. What I can do is I can say new node Mark. And then I got another place over here. All right. And over here, I can also say new node, and then Tom. It's a long expression, of course, and then null. All right, you see what I'm doing here? Okay. It's going to be a very, very long line where this guy here is going to be itself a chain of nodes that contains Mark. And this guy here, the next will just be Tom. This is going to work. All right? Guys, give a try this on Eclipse. Brian, that's what you're thinking about, right?
Yeah, but Giuseppe and I were wondering, you'd have to re-reference them in separate lines. Anyway.
Yeah, exactly. So the catch about this one here is, if you compare this version here, that's good observation. If you compare this version here versus, let's say, this version. In this version, you got both Mark and Tom. You know, they are referring to the node over here. But for this one here, not really. Okay, let's go a little bit more. You know, since I mentioned that, I better make sure you can feel as comfortable as possible. If I only talk about this part over here, right? Just this part, only up to here. I'm basically saying I'm creating Alan pointing to the new node. And then I got element here, which no surprise should be Alan. And then the next. So now I don't really create a node called Mark right away, right? In the intermediate stage. What I will do is I'm saying that this one here will just be a reference to some anonymous objects without any name, just object right away. So there is not another pointer here called Mark. Like previous. No, this no. That's the difference. Okay. And this one here is going to create the node elements and also next. And of course the element will be Mark right here. And then after that we're gonna get the pink, right? The pink one here is going to be the next. Right? You can see the next right here, right? The next is going to be just another node right here. The elements and also the next. And the element will be Tom, and then it will be null. So the difference is now we cannot really refer to this. There's no aliasing. So the only way I can refer to this node will be not Mark, but I got to say Alan.next. That's the only way. Yeah.
Quick question, sir. First, is it allowed for two or more nodes to point to the same node on the next, or no? So say, for example, both Alan
Yeah.
and Mark were pointing to Tom on next. Is that allowed? Or?
It is allowed. It wouldn't be forbidden. Okay, so it is okay. For example, what Diago was saying is it okay to have something like this? Jin. Let's say Jim also set its next to be here. Programmatically, absolutely, you can do that. However, conceptually, it may not be as clean. What do you really mean when two nodes point to the same node, right? So I would say conceptually, you want to avoid that. Yeah, good. First question. Yeah, just before I make a notes over here for everybody. So for this one here, so 2 nodes. Next, references aliased to the same object is possible, but not recommended. Possible, but not recommended. Right? Not recommended. I want to emphasize that. Right? Just confusing, right? Having 2 nodes pointing to the same node. Second question.
Second question would be, let's say you went ahead with this approach.
Yeah.
Making anonymous objects.
Yep.
Can you later on create a new object, also type node, that will point to one of those anonymous objects to have it as a reference? So say, for example, you say new node Jim, and then make it equal to Alan.next. Is that possible?
What you're saying, okay. What you're saying is, okay, so let me just create a new page, right? Interesting question here. Okay. What you're saying is, let me just erase that for now. Okay, so we can have a separate discussion. What you're asking is, can I write something like, for example, node, and then let's say Jin equals new node Jim, and here you simply say Alan.next. Is that what you're asking?
Yeah, maybe, or I'm not sure, maybe without the new node, but better just, instead of new node, just saying Alan.next.
Oh, okay, sure. Depends on what you want, right? Okay. Let's say, okay, maybe that's more complicated than you thought. Okay, so let's just go with what you said.
Yeah.
Okay, no problem. So let's say Alan.next. Oh, you know what? So maybe, oh, you're trying to kind of fix that reference issue, right?
Yeah,
Okay,
exactly.
now I got what you mean. Now I got totally what you mean. So maybe I'll just say Mark equals Alan.next. Okay, I like it. Yes, this is going to fix it because now Mark is going to be some name reference that point to that used to be the anonymous objects. Yes, so now from this point here, we can also refer to this object here, not just by Alan.next, but also Mark. Great, I like it. Yeah. I love you guys' question. All right, so very quick recap about your fellow students' question here and my responses. So when you, this is more like approach number 3, really, right? So you can have a single line of creation where you just can use anonymous objects. But the catch is you don't really have references to the intermediate anonymous object in the first place. So the solution, as Diago said, what you can do is you can just try to write some additional line to really name them individually. Right? You can get by still. All right? That's nice. Yeah, I'll make sure I also mention this to your fellow students next Tuesday, so it's fair. All right? Guys, any other thoughts? Yeah, Josh.
You said we should never really put 2 links to the same node.
Yeah, like 2 nodes having the next reference to the same node.
Would it potentially could you use that a secondary node to link to the halfway point so you don't have to scan through the whole list?
You know what? I know exactly what you mean. So Josh's question was, is it okay to say we kind of use a reference pointing to the halfway, like about n divided by 2 position? Yeah. But the problem is the list is dynamic. You don't really know how many nodes exactly. The node size, the list size can be 100, can be 200. You just don't know. It's hard to really set the half point. Let me get to it maybe a little bit later because we're going to talk about, in general, because the list structure is so dynamic, when you want to get somewhere to the middle, it's just not possible for you to store some cache reference for that. Just not possible. Yeah. Okay, I'll get there. All right, good. Let's now move on. All right. So now we learned about construction at the node level. I want to just do 2 pages very quickly. Let's say once we get this chain of nodes using whatever approach that works for you, right? We're just going to introduce one more level. Simply linked list. The way it's going to work is very straightforward. We got simply linked list over here. And remember, it has an attribute called head. And we're just going to use the mutator set head. Okay. So what we'll do is, to start with, we build the chain of nodes, first of all. We got this one, which is approach number 1 we saw earlier. And we'll get this chain of nodes. Let's say we got it already. And then we are going to create an empty simply linked list. And when I say empty, I want to clarify something also right away. So there is a critical difference between an empty list versus a null list. They are very different. Okay, I'll put it here. Okay, I'll put it right here. So when I say empty simply linked list, all right, let's say I got list number 1. That one point to over here. So I got simply linked list and it has a head. All right. When I first create, I'll say simply linked list, list number 1 will be new simply linked list. And you can think about this one here is like a default constructor, which means you're going to leave all the attributes to default value. So head is a reference, so it's going to be null, right? Default constructor, let's assume. So it's simply just going to be null, right? So this is an example of empty list, meaning that it's a list object there. It does exist, but it does not contain any nodes in the chain, just no nodes. So this one is something we call is an existing node, sorry, existing list, but empty. There's simply no nodes. Okay. You can think about empty chain of nodes. On the other hand, if I give you another object here, SLL, list 2, right? I explicitly initialize that to be null, or as your fellow student said earlier, what if I just declare that? As soon as I declare that, it also contains null, right? The way to visualize it would be for list number 2. Just points to null. So these two variables are very different, right? They are not the same, all right? It is not correct if you say list number 2 is empty. Empty means at least it exists, but it doesn't even exist, all right? So for list number 2, it simply stores some nonsensical address, so you will say that it's simply non-existing. All right, something very important to clarify, okay? Okay, let's now go back here. All right, so if we go back to approach number 1, so we're going to just build the chain of node this way, and then we're just going to create an empty list first. So we're going to create a list right here, empty to begin with. So I got simply linked list. I only got a head right now. All right, and then I got pointing to null. Okay, and let me copy that. I'm going to reuse it in just one moment. All right, that's this line here. And then I'm just going to see how I can connect the simply linked list to the chain of nodes. The way to do it will be I'm going to call the setHead method, right? I'm saying the head should be assigned to Alan. So the implicit this over here, since we are saying list, so this will be replaced by list. So list.head should be assigned to N. N will be just Alan, right? Right? It's going to point to wherever Alan is pointing to, like that. Right? That's how we set the head. You don't necessarily have to build a whole chain first before you set a head. You don't have to. I'm just showing you one example, right? It is okay to maybe start with maybe like an empty simply linked list and then call the various mutator. For example, like you want to add, maybe remove and also add first, etc. That's also possible, which we'll see maybe on Tuesday. Okay, okay, one more possibility. Still the same, really. We're just building the chain of nodes differently, right? That's approach number 2. Let's say we did the approach number 2 to build a chain. We still got the same chain, the same. And then I'm just going to call, again, the list constructor over here just the same way, right here. Right? That one there is going to create this empty list, as we saw earlier. And then I'm just going to set ahead in a similar fashion, right? Set ahead. That one there, head, rather than pointing to here, is going to point to right here. All right? Two different approaches. But of course, the more complicated bit has been understood already, which is about the two approaches of building the chain of nodes. Approach here and approach over here, right? Right here. And of course, the one you guys also learned about anonymous object, right? So 3 ways. Yeah, question.
Is there any exception thrown if you set the head as the last node?
Not quite. So the question was, if I say, oh, okay, I see what you mean. Let's say right now we're doing the right thing because we simply say set ahead to be Alan. Alan just happened to be the very first node. What if I say, rather than Alan, I set it to be, for example, Tom? There will not be any exception. This is more like a logical error. Okay? So I'm going to put it here. So let's say if I say list dot set head, rather than the very first node in the chain, I'll say Tom, let's say. Which means I'm going to set, rather than here, I'm going to set the head to be here, right? This is not going to trigger any exception, but you're going to run into logical trouble later. So that would mean if I want to say, I want to count the number of nodes in this particular list, I'm going to start with the head always. So if I start with this, I'm only going to count 1 node, which is wrong, because the chain of node over here is actually 3. Right? You're going to run into logical trouble. Okay. This will compile and run. But potential logical error later. Potentially logical error. Yeah, you really got to watch out for what you said. You don't necessarily always get compilation error or exception. There might be something that's kind of hidden somewhere in your code that's going to cause you trouble later. Question?
Yeah. If you set the head to null, will that be similar to like emptying the list, like basically?
Yeah, you can say that. Yeah. So also a good question here. You can think about if you somehow want to clear up the list, right? For sure, you can simply say, okay, I also write it out. You guys got very good question today. Good. So you can also say list the set the head over here simply just to null. So this will make sure the chain and the object is completely detached. Yeah. Whether or not this will be garbage collected is not your concern. Hopefully Java virtual machine will do that. It's kind of beyond our control. But at least as far as this list is concerned, once we set the head to be null again, we can actually set it to be another chain or try to build from scratch again. Okay. So this is more like clearing up the list. Okay, which is also very nice. Okay. Yeah.
Sorry, second question.
No worries.
Does the simply linked list class only has the default constructor, empty constructor, or can you pass it?
Okay, good question. So for now, I think for the simply linked list, just for our purpose, I didn't even have the constructor explicitly defined, just default constructor. I would say once you get your programming assignment, I believe it say that you shouldn't really try to modify the simply linked list. But I'll say later on, if you want to build your own simply linked list class, feel free to define more constructor that's overloaded. That's fine. Yeah. All right. All right, guys. So next one there, let's see some algorithm on simply linked list, right? Let's see that. Let's do this one here, and this will take a little bit of time to really give you the tracing, idea, visualization, and some lesson, and then we'll take a short break afterwards, right? Hopefully 10 minutes or so. Okay. Potentially we could finish a little bit fewer pages today because you guys got more questions, which is okay. I also need to mention, summarize the point to your morning fellow students as well on Tuesday, so they also get the same information. All right, so we have covered these So let's now talk about counting the number of nodes, right? It's a very simple algorithm, but I would say that one there really shows us some very useful patterns that you want to use, right? I think that's really the main idea. This will be one, and then the next one, which we'll take a look after the break, is about how you can get the tail of the list, right? So both are nice. All right, so we want to return the number. For now, let's temporarily. Sorry, let me take it back. The problem is we want to return the number of nodes currently stored in the syncly linked list. So we're adding a method into the syncly linked list class. All right, that's what we're doing. Okay, and I can show you the code right away. That's okay. It's a simple one. We want to dive into it right away. First of all, let's now be very clear about where this method is defined. Okay, so this is a method that's defined in syncly linked list class, not the node class. A syncly linked list method. All right, that's the one. And let's have a very quick walkthrough about the code and what's really involved. We basically create two variables over here. We got a variable called size. We got a variable called current. And current, I think for those of you who took a 2031 or 2032, for those of you who may have seen some linked list in C, they might be using the same convention, right? Like a current, maybe. Okay? If no, now you see it. We got two variables over here, right? We kind of initialize them, and then we got some while loop, right? So whenever you see a while loop, right now, for the linked list, you'll be especially useful. Whenever you see a while loop, you can see the condition here. Current not equal to null. This one tells you, as long as this condition here is true, you're going to keep iterating. But I want to tell you that sometimes it might be also very useful to think about when does the loop exit. The condition will just be the logical negation of this condition here. Well, I'm going to write it down. This one tells you the loop will keep running as long as current is not equal to null. Alternatively, you can think of it like it will exit when the negation of this, which will be equal, right? Negation will be current equals null. Just keep this in mind, and then we'll see exactly how useful this can be. So current equals null is a very common exit condition for the while loop. If you want to scan the list from left to right, it's a very typical pattern if you want to design algorithm on that. Another thing to point out, once we study the two algorithms today, you can also think of the current here. In some way, it's a bit like a loop counter. So whenever you talk about while loop or for loop, you declare some integer I or j, I, j, k, the loop counter. So there is not really a loop counter per se, for linked list, because you don't have indexing for the linked list. But current here is more like a loop counter. You want to keep track of where you are in the loop for the list. So think about it. It's a little bit like loop counter. So current tells you where you are exactly in the middle of the list. And we'll see that when we trace the code. All right. And then in the body of the loop over here, we are just going to update the current in each iteration by changing current to its next. For example, if current is right now pointing to here in the middle, what does it really mean when I say current equals current.next? Current.next is right here. Current assigned to current.next, rather than pointing to here, is now going to point to its next. So we're basically moving the current pointer from to the right by one position, right? It's a very typical pattern, right? It's almost like I++, right? If you think of it. And then not only that, we're going to do that, also we're going to do size++, right? Update the counter as well, okay? Even before, so maybe not. Let's fill the table first. I think that'll be better. Let's now trace the code. Let's now, first of all, look at the code that's going to prepare us for the loop. So let's say look at line number 2 and 3, only these two lines, right? Where we're going to initialize the size to be 0 and current to be the head. All right? So you can think about the size is going to be just 0 in the beginning. And also we got current pointing to the head. Right? Remember the head of the list is pointing to Alan. We just let current point to the same node, right? Exactly like that, right? So you can think about this, and this is a setup right before the first iteration. So what I will do is I'm just going to trace the code here in the table just to show you precisely what's going to happen. I got current right now is Alan, right? Alan node. And then if I try to check this condition over here, the while loop for the first time, Alan not equal to null, right? Because current is Alan. Alan apparently is an existing node. So that one not equal to null is true. True means we are going to execute the body of the loop for the first time. All right. And then for these two, I'm just going to show to you what's going to happen, right? For these two, current is assigned to current.getNext. So that means current, rather than pointing to here, is going to point to current.next. So that means current is now changing to here. And then we're going to increment the size from 0 to 1. All right, so that's the field in the table as well. So after this first iteration, current will now be just mark, right? You can see current is now pointing to where mark is pointing to. So we'll say current will just be equal to mark. And the size is just 1. So this is at the end of the first iteration. Okay? So at the end of the first iteration, we are now basically finished processing the first node. Okay? Let's now continue. And then we're going to now check the while loop for the second time to see whether we should execute for the second iteration. Right? So current right now is mark. And when we check this condition here, current not equal to null, so mark not equal to null should be true. So keep iterating for the second iteration. And then for the second iteration, let me change the color here. So we're going to execute these two lines again, right? So we're going to change the current and also going to change the size. Current, rather than pointing to here, is now going to point to its next. So current is going to be here. Right? And then the size is going to be incremented from 1 to 2. Right? And at the table, we can simply say current right now will be just Tom. And size will now be 2. Not done yet. Not yet. Because current got to be null before when we exit the loop. Not yet. We're getting there. All right, so now we're done with the second iteration. So now we're going to check the condition again. So we're going to check the while condition here for the third time. So current right now is Tom. So Tom not equal to null is equal to true, right? And then we're just going to execute line number 5 and line number 6 for the third time. That one there, first of all, we're going to say current, rather than pointing to here, its next will just be null. So basically set current to be null. And then you're going to increment the size from 2 to 3. So current is now going to be equal to null. And then the size will be 3. All right, finally, when we check whether we should continue with the while loop for the fourth time, current right now is null. So we are checking null not equal to null. Apparently, that one there is false. Exit from the loop. No further iteration. So this guarantees termination, right? So current here, we are assuming that if you go from left to right, then eventually current is going to be null. So we can exit from the loop. All right, any question about tracing? Right? So this one here is pretty straightforward. You just gotta, I wouldn't say straightforward if you're seeing it the first time. Take some time to really digest it. Also, you want to pay more attention about how the two variables, size and current, somehow got updated in each iteration. Look at that more closely. In the next example we're going to look at, when we try to find the tail, there will be 2 pointers going together. That's going to be even more interesting. But before that. All right, so let's now figure out the running time. Right? To approximate it, we basically got to figure out, first of all, how many times are we going to run the iteration. And then For each iteration, we can see obviously it's going to be constant, right? You can see just variable assignments, some attribute access to the next, and some variable assignment. Very easy, right? We just got to figure out the number of iterations. And we have that information already. If you look at just this one here. Oh, let me just do it again. If you look at the size column over here, right here, right? You can see we got one iteration, second iteration, and third iteration. So the number of iterations here simply corresponds to how many nodes you have in the chain, which is the input size, really. All right? So what we got is the number of iterations will just be equal to the number of nodes in the chain. And just the number of iterations will be linear. All right, first of all, the iterations itself will be linear. And given that each iteration is going to take constant amount of time, so n times 1, n, right? Overall, big O of n times 1 will just be big O of n. So this is the number of iterations, and this is basically line number 5 and line number 6. Right? Just to be a little bit more detailed here. That's the final answer. Right? Yeah, for this example here, try to understand how to use a current. It's going to be very useful for your assignment and test, and also how to introduce like extra variables to help you, and also how to trace, and also figure out the running time. Right? There are many things we can learn from this small example here. Any question? Why don't we take a very short break, 2 or 3 minutes, taking attendance, and then we'll come back. Okay. Okay. So before the break, we saw that get a number of nodes to count, and we're going to see another problem. But in the slide, of course, we finished slide 15 already. You can take a look. So the next problem will be, oh, by the way, if you do some contrast, if you simply want to write a loop to count the number of nodes, it's going to be linear. What about array? What will be the cost for getting the size of the array? Constant, a.length, easy. However, as a very quick look ahead, we're going to see some very good principle called trading space for time later. If you're willing to somehow introduce some extra data, but there will be some catch. But if you're willing to introduce the data and taking the catch, you can actually make the linear time get sized into constant time. I'll talk about it. Okay. But before that, let's see one more example of the algorithm. That one there I can also give you a little bit more inspiration when you do the linked list algorithm. All right, we did the tracing also before the break, and the new problem is here. Okay, finding the tail. It's actually a very similar problem here. The thing is, now we don't really want to just return an integer indicating how many nodes we have. We want to return the reference of a node, and that node should be the last node in the chain, the tail. Right? That's something we want to do. All right, let's take a look. All right, again, I'll give you the code right away. Not that many lines. And it does share lots of similarity to the get number of nodes that we talked about before the break, right? So I'm going to present it in a slightly different way, a little bit quicker, right, to do the tracing. You really want to see, what I really want you to see is how the current and the tail, these two variables are kind of kept in sync somehow. I'm going to leave the tracing table here clean, and for those of you who want to practice tracing, you should really try. Okay, it's going to be helpful as well. I'm going to highlight all the lines relevant to the current in green. So I got this line here about the current. I got this line here about the current. I also got this one here about the current. So you can think about the current itself, as we said earlier, it's like a loop counter. It's going to limit about how many iterations it's going to run for the while loop. Because the current is going to start with here and keep moving to the right until it's moved just to the null, and then we stop. Right? So it guarantees termination. That's the role for the current. And sometimes you might see some scenario where you might need current 1, current 2. You might want to keep 2 references about where things are. You might see things like that, right? For the more advanced example, right? Just be a little bit flexible and creative. The second variable we have now, rather than integer, is going to be another node. That one is called the tail. Here, here, and eventually we just want to return the tail, right? Eventually. So there are only two lines over here. That's kind of interesting, all right? So the idea would be initially the tail is going to be null, not existing. And then every time before we try to move the current to its next, we want to capture the old value for current into tail. That's exactly what I meant over here. It's not too bad, okay? Let's say right before the loop, what do we have for the first iteration? Right before the loop, right here, okay? What we have is we got current right here. Current right here. And the tail will just be null. All right? And there is going to be one thing that's going to be maintained. The current is going to be one node ahead of the tail. Right now, current is the first node. Tail is nothing. It's like a one node ahead. So if current happen to be pointing to the second node, then tail will be the second node. Sorry, the first node. One node behind. But I'm going to show you, right? I'll write it down. The current is always one node ahead. One node ahead of the tail. We can say head, or we can say the tail is one node behind the current. That's another way to say it, right? Up to you. Got current here, and then I got the tail over here. All right, good. Let's see. For the very first iteration, you can see that current is not equal to null, apparently, right? So we're going to execute these two lines for the first iteration, right? So for the first iteration, we're going to actually change, first of all, before we move the current to over here, before we do that, we're going to capture the current value of current into tail. What it does is like this. So that one there is going to, first of all, the tail, rather than pointing to here, is now going to point to wherever current is pointing to. And then we're going to execute this line to move the current to the right by one position. That means current is now going to point to here. So the blue here is the first iteration. All right? So I'm just going to try to see if I can make a little bit more. So think about this. These two arrows are what we have to do for the first iteration. All right? And to check to see whether we're going to run for the second iteration, we're going to check for the current. Current is right now here. Is it equal to null? No. So, second iteration. For the second iteration, we are going to basically execute these two lines again, right? First of all, tail equals current. Tail, rather than pointing to here, is now going to point to wherever current is pointing to, right? You can see current is actually pointing to here. And then we're going to change current to the right by one position. So current, rather than pointing to over here, is now going to point to right here, right? You can see again, the tail is one node behind the current. All right? Question?
Instead of setting tail equal to current every single iteration, can you put it outside of the condition?
Let's talk about modification a little bit later. Let me finish tracing first, and then we'll talk about that. Yeah, give me one moment. Okay? So at the end of the second iteration, let's see what we have, right? Let's, okay, let's say here, right here. Okay, so this part over here is about the second iteration. All right, we're almost there. And then for the third iteration, should we execute it? So current over here is Tom, not equal to null. So of course, we need another iteration, right? So let's see, we have, let's say, orange. we're going to execute, first of all, this line here. Tail will be current. So tail, rather than pointing to here, is actually going to point to wherever current is pointing to, right here, right? Because current right now is pointing to here. And then we're going to move the current to the right by 1 position. Rather than pointing to here, it's now going to point to right here. You can see current dot next will just be null. So this will also be pointing to null. So that's a last iteration, okay? Third iteration as well. Let me annotate it, and then let me make some quick conclusion, and I'll get back to your fellow students' question. Not yet. Okay. So this one here is a third iteration. Again, you can see very easily the number of iterations that we need. You can see the first, the second, and also the third correspond to how many nodes we have in the chain, right? Similar. So I think for this example here, you want to focus more on how exactly the current and the tail are moving, right? That's really the point to really focus on. Let me talk about the running time very quickly, and I'll get to your question. So it's going to be dominated by this while loop. And the number of iterations, as I illustrated, is going to be corresponding to the number of nodes in the chain. So the number of iterations will be just the size of the list, big O of n. And we know that for line number 5 and line number 6, the body of the loop just constant, right? Overall, it's going to be big O of n times 1. And the 1 over here is line number 5 and line number 6, which will be big O of n overall. Yeah, question again, please.
I was just wondering if you could, instead of setting tail to current every single iteration, take it out of the loop and change the while conditions to use current dot get next not equal to null.
It would be possible, actually, to somehow get rid of the tail variable somehow and just somehow return the current instead as the tail. So the reason that I kind of introduced like an extra variable just to show to you, in some cases, it will be beneficial to have multiple variables traversing the list at the same time. But I think for this particular problem here, you can definitely try. Only use the current and then return somehow its value as the tail at the same time. But I think at this one, the focus is a little bit different. We want to see multiple variables traversing the list at the same time to see how they evolve together. Yeah. Okay. I can put down as a short exercise here if you guys want to try. Use the current only to implement getTail. It's definitely possible. All right, guys, feel free to give it a try. But I would say if you want to introduce some extra variable just to help you a little bit, help you better understand about how things are going, you can also feel free. All right, good. All right, if this is good, I will talk about maybe, okay, at least one more thing. So we'll be just one example behind the morning section. Okay, not too bad. Okay. All right, so let's now go back to the slides and let's go over something here. So we talk about the tail over here, and the running time is simply linear. All right, question for you. If I want to do the corresponding operation in the array, how do I find the tail of the array? Huh? Yes, go to that particular index, right? Very good. All right, so you will see that one there, we know that's constant operation. Exactly. Okay, very good. So you can see for the size and for the tail, seems to be very expensive in the linked list, but very cheap in the array. That's what we have seen so far. However, there will be something you can do at the programming level to make things a little bit cheaper. But nothing does not come with a cost. I also need to mention the price you're going to pay as well. All right, let's talk about this one here. All right, well, you can go over the tracing table here if you do the exercise. All right, can we do better? Yes, we can, but you got to make sure you know what the catch is. Why do we want to make it efficient to maybe get access to the tail or want to count the number of nodes? For example, let's say you got a service queue somewhere and you want to get to the last customer in the service queue. Maybe you want to move them somewhere, right? Or maybe you simply want to see if the service queue is actually full. So using a linked list is a very common data structure for implementing a queue, right? Just some usage scenario here. And we're going to introduce something called trade the space for the time, right? Let's talk about this at least before the end of today, all right? So let's talk about one more. And this will be some self-engineering principle, which we're going to see at least another 1 or 2 times in addition to this. Well, you can definitely try to practice this whenever you can. Trading space for time, in more layman's term, is like this. All right, trading space for time. Sounds a bit fancy, okay? Basically, you say, I can afford to waste some more spaces. I want to waste more memory space to make the subsequent computations cheaper. Computations cheaper. Right? You can think about the space, of course, is the memory space. And the time is about the computation. Computation could be what you got to implement using a while loop for the getSize and getTail. Okay? So rather than having to write expensive computation, which would take linear time, I'm going to somehow waste because I can afford. I want to waste some space to make it cheaper. Okay? That's exactly what I mean. Let's see this example here where we assume we only got a head attributes, right? The way we're going to do it is, let's say we want to store more data, more attributes for each linked list objects. So visually, I'm just going to extend the object over here by 2 attributes, all right? 2. So after this discussion, starting from next Tuesday when we come back here, okay, we're going to assume for your simply linked list class, we got 3 attributes. We got a head, we got a tail, and also we got a size. All right. And the tail, of course, should really point to the last node right here, right? Right here. And the size should be 3 at the moment, right? So they should be updated whenever you can. Let's talk about the exactly what's the advantages for trading the space for time, and then I'll talk about the catch. Okay? And the catch is something we have to see some code to really appreciate it. But that's something we'll look at that on Tuesday. But let's go over principle. So what we have, now make sure. Okay, 4 minutes should be enough. Okay, let's go over this principle quickly. So we got simply linked list class. And we assume that we got 3 attributes here. We got the head, and we got the tail, and we got the size. And think about these are all the attributes. All right, these are all the attributes. Since we're getting more attributes, that means we're wasting more space, more cost of the space. That implies more cost of space. Right? Straightforward. You can introduce as many attributes as you like to waste the space, hoping that it's going to improve the computation later. On the other hand, now let's say I got all these, head, tail, and size, as attributes. The consequence is, if I create, let's say, simply linked list, some empty list to begin with, equals new, and SLL. Let's say I do something here, simply I kind of construct a non-empty list, maybe of certain size, right? And now I want to know where is the tail and where is the size. I can simply say list.tail. I can also say list.size. Both of them will just be attribute accesses, right? Each one of them, which is going to be constant time. Both of them will just be bigger of 1. And if you like, I'll put down some notes here. So these will be just some attribute accesses. Attribute access. And if you're able to somehow turn a while loop into an attribute access, you're getting less cost about computation. For running time. Or thinking another way, we're basically turning loops into attribute access. Attribute access, right? And a final thing, okay, maybe about 1 minute, okay? What's the catch? There's nothing that doesn't come with a price. The price we gotta pay is somehow our code for algorithm for syncly linked list from now on is gonna be more complicated. In the sense that whenever you want to implement an algorithm, you always want to think about whether it's going to impact head, tail, or size, and do the corresponding updates. There's no way around. You don't want these three values to be inconsistent. All right, I'm going to write down the catch and then highlight something, and then we'll talk more. Okay. So catch right here. For methods, okay, guys, you can give me just 1 minute, I'll get this done. For methods that might impact the head, tail, or size of the syncly linked list, the bodies of the implementation must update them, the attributes, properly. Right, let me do some quick highlights, and then we're done. Okay, so the highlight here is really about, for methods, not really all the methods. You gotta judge which method should really do such updates. And then we're talking about head, tail, and size for now, and you may want to do the updates properly. Right, so we're gonna talk about more methods on Tuesday. We'll see how these can be implemented. All right, thank you so much. Get on with your assignment number 2. All right, make sure you start. See you next week.